White phosphorus is a soft, waxy, and translucent solid. It is insoluble in water, but soluble in carbon tetrachloride or carbon disulfide. It dissolves in boiling caustic soda in an inert atmosphere to give phosphine and sodium hypophosphite. It is highly toxic and extremely reactive. It exists as tetrahedral P4 molecules. These molecules are held together by weak van der Waals forces of attraction. Hence, it has a very low melting point of 44 degrees Celsius. As you can see from the structure, each phosphorus atom is covalently bonded to 3 other atoms of phosphorus. The bond angle in a P4 molecule is 60 degrees, which is much less than the expected or theoretical bond angle. You know that when pure p orbitals overlap, the theoretical bond angle expected is 90 degrees. This angular strain in the molecule makes white phosphorus unstable and therefore highly reactive. Therefore, white phosphorus ignites spontaneously in air at about 35 degrees Celsius. That is, at a temperature slightly higher than room temperature, to form phosphorus pentoxide. The equation for this reaction is shown here. This angular strain in the molecule makes white phosphorus unstable and therefore highly reactive. Therefore, white phosphorus ignites spontaneously in air at about 35 degrees Celsius. That is, at a temperature slightly higher than room temperature, to form phosphorus pentoxide. The equation for this reaction is shown here. Owing to its high reactivity, white phosphorus is stored underwater. White phosphorus glows in the dark. Do you know why? In contact with humid air, white phosphorus gets oxidized. This reaction is associated with the emission of light. As a consequence, it glows in the dark. Note that the emission of light or electromagnetic radiation during a chemical reaction is called chemiluminescence. Thus, white phosphorus exhibits chemiluminescence. When white phosphorus is heated to about 250 degrees Celsius in the presence of sunlight, a stable allotrope of phosphorus is obtained, which is called red phosphorus. Red phosphorus is an iron-grey, lustrous crystalline solid that is odorless, non-toxic, and insoluble in water as well as in carbon tetrachloride. It doesn't dissolve in boiling caustic soda, but dissolves in alcoholic potash. It exists as a polymeric solid. It means that red phosphorus consists of a chain of P4 units that are linked together by single covalent bonds. Hence, it is stable under normal conditions and doesn't ignite in air. It is therefore not stored in water. It undergoes combustion only when heated to about 400 degrees Celsius. Note that red phosphorus doesn't exhibit chemiluminescence. The other principal allotrope and thermally the most stable is black phosphorus. It is a highly polymerized form of phosphorus. It has a layered structure. It exists in two forms, namely alpha-black phosphorus and beta-black phosphorus. When white phosphorus is heated at 473 Kelvin, under high pressure, it forms beta-black phosphorus. It doesn't ignite in air up to 673 Kelvin. On the other hand, when red phosphorus is heated to 803 Kelvin in a sealed tube for a sufficiently long time, it forms alpha-black phosphorus. Alpha-black phosphorus has opaque monoclinic or rhombohedral crystals, while beta-black phosphorus consists of corrugated sheets that result in the formation of flaky layered crystals. Alpha-black phosphorus doesn't conduct electricity, but beta-black phosphorus does. You know that phosphine is a hydride of phosphorus. It was discovered by Cbse in 1783. It is formed in the soil by the bacterial reduction of phosphates. Let us begin our study with the methods to prepare phosphine. Phosphine can be obtained by the hydrolysis of metallic phosphides with water or dilute mineral acids like hydrochloric acid or sulfuric acid. Calcium phosphide or sodium phosphide, on being hydrolyzed with water, produce phosphine. Similarly, when aluminium phosphide is hydrolyzed with hydrochloric acid, it gives phosphine. The equations for these reactions are shown here. Phosphine is also prepared by hydrolyzing white phosphorus with a concentrated solution of sodium hydroxide. This is the laboratory method to prepare phosphine. Let us take a quick look at it. A concentrated solution of sodium hydroxide and white phosphorus is taken in a round-bottomed flask, as shown in the apparatus arranged here. The reaction is allowed to take place in an inert atmosphere of carbon dioxide or oil gas, because phosphorus would otherwise react with oxygen and lead to an explosion. The contents of the round-bottom flask are heated to produce phosphine gas. This gas is delivered into a trough of water. Bubbles of the gas catch fire as soon as they come in contact with air to form rings of smoke, called vortex rings, as shown here. This indicates the presence of highly inflammable phosphorus dihydride or diphosphine as an impurity in phosphine. Are you aware of this fact? The flickering light in marshy places is believed to be corpse candles or ghostly lights. However, in fact, the origin of the flickering light, called will-o'-the-wisp, is due to the spontaneous inflammation of diphosphine present in marshes. The phosphine obtained in the process is purified by absorbing it in anhydrous hydrogen iodide that forms phosphonium iodide. This, on heating with potassium hydroxide, evolves phosphine gas that does not have diphosphine. Pure phosphine can also be obtained by using alcoholic potassium hydroxide instead of an aqueous sodium hydroxide solution. This is because diphosphine is insoluble in alcohol. Diphosphine can also be removed by passing the gas through a freezing mixture in which diphosphine condenses while phosphine doesn't. Activated charcoal or phosphorus pentoxide can be used to adsorb the liquid hydride diphosphine from phosphine gas. Next, let us see how phosphine differs from ammonia as far as bond angle is concerned. You already know that ammonia has pyramidal geometry with a bond angle of 107.8 degrees. Similarly, phosphine is also expected to have pyramidal geometry with nearly the same or similar bond angle. However, the bond angle in phosphine is only 93.5 degrees. How do you account for this? Try to explain this variation by comparing the electronegativities of the central atoms in their respective hydrides. You know that phosphorus has less electronegativity than nitrogen. As a consequence, the electron density around the central atom, phosphorus, is less concentrated as compared to nitrogen in ammonia. In other words, the bond pair of electrons is much farther away from the central atom in phosphine than it is in ammonia. As a result, the lone pair causes even greater distortion in phosphine. Thus, the bond angle in phosphine decreases to 93.5 degrees. Moreover, the bond angle of 93.5 degrees suggests that the orbitals used for bonding are close to pure p orbitals. Let us first study the properties of phosphine. Phosphine is a colorless and extremely poisonous gas that smells like garlic or rotten fish. Unlike ammonia, it is slightly soluble in water, and the aqueous solution is neutral. It is more soluble in carbon disulfide and other organic solvents. The melting and boiling points of phosphine are much less than that of ammonia due to the absence of hydrogen bonding. It condenses to a colorless liquid at -87 degrees Celsius and freezes at -132 degrees Celsius. Phosphine acts as a Lewis base analogous to ammonia due to the presence of a lone pair of electrons. However, it is a weaker base than ammonia because its central atom, phosphorus, is larger in size and less electronegative. Its basic character is evident from its reactivity towards anhydrous halogen acids such as anhydrous hydrogen iodide. Phosphine combines with hydrogen iodide, thereby acting as a Lewis base by donating its lone pair to form phosphonium iodide salt. Talking about phosphonium salts, the phosphonium ion has a structure similar to the ammonium ion as shown here. Do you know why the bond angle of phosphonium ion is higher than that of phosphine? Try to answer this question on your own before looking at the answer. The central phosphorus atom is tetravalent in phosphonium ion and trivalent in phosphine. This indicates that there are 1 lone pair and 3 bond pairs in phosphine. While all the 4 are bond pairs in phosphonium ion, you know that the magnitude of repulsion between a lone pair and a bond pair is greater than between 2 bond pairs. Hence, the extent of repulsive interaction in phosphonium is less than in phosphine. As a result, the bond angle in phosphonium ion is greater than in phosphine. Pure phosphine is non-combustible at normal conditions, but catches fire when heated to about 150 degrees Celsius to form phosphoric acid. When phosphine is heated to about 440 degrees Celsius in an inert atmosphere, or when it is subjected to an electric spark, it decomposes into its constituents, namely red phosphorus and hydrogen. Also, an aqueous solution of phosphine decomposes in the presence of light into red phosphorus and hydrogen. It burns with an explosion when it comes in contact with even the smallest amounts of oxidizing agents such as nitric acid and chlorine gas. Nitric acid oxidizes phosphine to phosphorus pentoxide and itself gets reduced to nitrogen dioxide as shown in the equation here. Similarly, the equation corresponding to the oxidation of phosphine in the presence of chlorine is also shown. When passed through aqueous metallic salt solutions such as copper sulfate, silver nitrate, and mercury chloride, phosphine gas precipitates the corresponding metal phosphides. As can be seen from these equations, copper phosphide is precipitated from copper sulfate, silver phosphide from silver nitrate, and mercuric phosphide from mercury chloride. You know that the reducing power of the hydrides of group 15 elements gradually increases on descending the group. Hence, the reducing power of phosphine is greater than its analogue ammonia. It reduces auric chloride to metallic gold, as shown in the equation here. Let us now turn to the uses of phosphine. The hydrolysis of calcium phosphide finds use in the manufacture of Holmes signals. A mixture of calcium phosphide and calcium carbide is taken in a container and sealed. When needed, the container is pierced and thrown into the sea. As water enters the container, it reacts with the mixture and produces brilliant flashes of light, a bright luminous flame which serves as a signal to approaching ships. The bright luminous flame is due to the formation of phosphine and acetylene on the hydrolysis of calcium phosphide and calcium carbide. Note that the spontaneous flammability of phosphine is due to the presence of diphosphine. The same reaction is also used in smoke screens. The phosphine obtained catches fire and produces the required smoke. You know that phosphorus forms two types of halides, namely px3 and px5. Here, X represents a halogen, which may be fluorine, chlorine, bromine or iodine. Of these, chlorides are more common. These chlorides are covalent in nature. Let's first study the preparation and properties of phosphorus trichloride. In the laboratory, phosphorus trichloride is prepared by heating white phosphorus in a current of dry chlorine. Let's take a quick look at the method of preparation. The apparatus required is arranged as shown here. White phosphorus is placed in a retort and gently heated over a water bath. A current of pure and dry chlorine gas is passed over the white phosphorus. Phosphorus trichloride distills off, and the vapors are condensed in a water-cooled receiver. Phosphorus trichloride can also be prepared by the action of white phosphorus on thionide chloride. The equation for this reaction is given here. Talking about its structure, the central phosphorus atom in phosphorus trichloride undergoes sp3 hybridization with 3 bond pairs and 1 lone pair of electrons. On account of this, it has a pyramidal shape. It acts as a Lewis base due to its ability to donate its lone pair of electrons to other electron-deficient ions or molecules. Let us now turn to the properties of phosphorus trichloride. It is a colorless liquid with a pungent smell. It has a very low boiling point of 74 degrees Celsius. It reacts violently with water and gets hydrolyzed to form phosphorus acid and fumes of hydrochloric acid. As a consequence, it fumes in moist air. Similarly, it reacts with organic compounds that contain hydroxyl groups such as acetic acid and ethyl alcohol to form phosphorus acid as the main product. Let's now move on to the preparation and properties of phosphorus pentachloride. In the laboratory, phosphorus pentachloride is generally prepared by passing excess chlorine into a solution of phosphorus trichloride in carbon tetrachloride. Phosphorus pentachloride can also be prepared by using these methods. Let us now discuss the properties of phosphorus pentachloride. Phosphorus pentachloride is a yellowish-white crystalline powder. It sublimes on heating at 160 degrees Celsius. On strong heating, phosphorus pentachloride dissociates into phosphorus trichloride and chlorine as shown in the equation here. Phosphorus pentachloride reacts violently with excess of water to form phosphoric acid. In other words, phosphorus pentachloride, on complete hydrolysis, gives phosphoric acid. Note that it forms phosphoryl chloride or phosphorus oxochloride and hydrochloric acid when equimolar amounts of phosphorus pentachloride and water are used. In other words, when water is taken in small amounts, the products formed are phosphorus oxochloride and hydrochloric acid. Now, write a balanced chemical equation for the hydrolytic reaction of phosphorus pentachloride with heavy water. Try this on your own before looking at the answer. Here are the balanced chemical equations for the reactions of phosphorus pentachloride with small amounts of D2O and excess of D2O. Just like phosphorus trichloride, phosphorus pentachloride also reacts with organic compounds that contain hydroxyl groups. It replaces the hydroxyl groups in the compounds with chlorine atoms. For example, the hydroxyl groups in ethyl alcohol and acetic acid are replaced by chlorine atoms to form chloroderivatives, namely ethyl chloride and acetyl chloride, as shown here. When heated with finely divided metals such as copper, silver, and tin, phosphorus pentachloride forms the corresponding chlorides, namely cuprous chloride, argentous chloride, and stannic chloride. Next, let us look more closely at the structure of phosphorus pentachloride. The central phosphorus atom in phosphorus pentachloride undergoes sp3d hybridization. From the VSEPR theory, you know that since all the 5 electron pairs in these hybrid orbitals are bond pairs, the geometry of the molecule is trigonal pyramidal, as shown here. Of the 5 hybrid orbitals, 3 occupy equatorial positions, while the remaining 2 occupy axial positions. As a consequence, 2 different bond angles are observed in the molecule. They are 120 degrees and 90 degrees. Also note that the 3 equatorial PCl bonds are equivalent with bond lengths of 202 picometers, while the 2 axial PCl bonds are longer than equatorial bonds with bond lengths of 240 picometers. Trigonal bipyramidal geometry is observed only in its liquid and gaseous states. However, in the solid state, it exists as a salt, that is, as an ionic solid in which the cation tetrachlorophosphonium is tetrahedral, while the anion hexachlorophosphate 5 is octahedral, as shown here. Phosphorus forms a number of oxo acids, such as hypophosphorus acid, orthophosphorus acid, pyrophosphorus acid, hypophosphoric acid, orthophosphoric acid, pyrophosphoric acid, and metaphosphoric acid. The table here lists the formula and oxidation state of each of these oxo acids. Phosphorus usually exhibits an oxidation state of either +3 or +5 in its oxo acids. Note that the oxidation state of phosphorus in hypophosphorus acid is +1, while it is +4 in hypophosphoric acid. The oxo acids in which phosphorus exhibits lower oxidation state of +1 or +3 constitute the phosphorus acid series, while the ones in which phosphorus exhibits higher oxidation states of +4 or +5 constitute the phosphoric acid series. Let us first look at some methods to prepare oxo acids belonging to the phosphorus acid series. Hypophosphorus acid, also called phosphinic acid, is prepared by the alkaline hydrolysis of white phosphorus. When white phosphorus is heated with an alkali solution, like barium hydroxide, it forms hypophosphite. This is further treated with dilute sulfuric acid to recover the acid. The hydrolysis of phosphorus trioxide or phosphorus trichloride forms orthophosphorus acid, phosphonic acid, or simply phosphorus acid. Orthophosphorus acid can be conveniently prepared by passing chlorine gas through water containing molten white phosphorus. The phosphorus trichloride so formed is instantly hydrolyzed to give orthophosphorus acid. Orthophosphorus acid, when treated with phosphorus trichloride, gives pyrophosphorus acid. Let us now discuss some methods to prepare oxo acids belonging to the phosphoric acid series. Hypophosphoric acid is obtained by the alkaline hydrolysis and oxidation of red phosphorus. As shown by these set of equations. Orthophosphoric acid, also called phosphoric acid, is industrially the most important oxo acid of phosphorus. It is prepared by dissolving phosphorus pentoxide in water and then boiling the solution. The stepwise process of the hydrolysis of phosphorus pentoxide is represented here. When phosphoric acid is heated gently to about 220 degrees Celsius, it loses water molecules to form pyrophosphoric acid. Pyrophosphoric acid or orthophosphoric acid when heated to red hot, forms metaphosphoric acid. Crystalline phosphorus acid, on being heated with bromine in a sealed tube, gives metaphosphoric acid. Note that metaphosphoric acid exists as a polymer. Cyclotrimetaphosphoric acid and polymetaphosphoric acid are some polymeric forms of metaphosphoric acid. You know that phosphorus forms a number of oxo acids, such as hypophosphorus acid, orthophosphorus acid, pyrophosphorus acid, hypophosphoric acid, orthophosphoric acid, pyrophosphoric acid, and metaphosphoric acid. Examine the structures of the oxo acids given here. Now, try to list the characteristic bonds and the number of these bonds present in each of these oxo acids before you take a look at the table that has the relevant data. The table here lists the characteristic bonds and the number of these bonds in each of these oxo acids. Let us now discuss the common and some important features of the structures of the oxo acids of phosphorus. In all of these oxo acids, the central phosphorus atom is surrounded tetrahedrally by other atoms. At least one P double bond O and one POH bond are essentially present in all of these oxo acids. Note that the double bond is formed as a result of the P-pi back bonding. However, pH bonds are present only in the oxo acids belonging to the phosphorus acid series. Note that in hypophosphoric acid, an unusual PP bond is present. Only the hydrogen atoms that are attached to oxygen in POH bonds are ionizable. And impart acidic character to the compound. Thus, the number of ionizable hydrogens determines the basicity of an acid. On the other hand, the pH bond is not ionizable. The pH bonds found in the oxo acids of the phosphorus acid series have reducing properties. In other words, the hydrogen atoms attached directly to the phosphorus atom are not ionizable and confer reducing properties to the compound. Examine the structures of hypophosphorus acid and orthophosphoric acid. Of these, which oxo acid can reduce silver nitrate to metallic silver? Also justify your answer. Try to answer this question on your own before looking at the answer. It is apparent from the two structures that hypophosphorus acid contains two pH bonds. Why? There is no pH bond in orthophosphoric acid. Hence, hypophosphorus acid reduces silver nitrate to metallic silver, as shown by the equation here. Similarly, orthophosphorus acid and pyrophosphorus acid which belong to the phosphorus acid series, are good reducing agents. Orthophosphoric acid is a tribasic acid. Can you justify this statement before looking at the answer? You know that only the hydrogen atoms that are attached to oxygen in POH bonds are ionizable and impart acidic nature to the compound. From the structure of orthophosphoric acid, it is evident that it has 3 ionizable hydrogen atoms. Hence, it is a tribasic acid. Note the basicity of the remaining oxo acids based on the number of ionizable hydrogens that are listed in the table here. The oxo acids in lower oxidation states of phosphorus +1 and +3 tend to disproportionate to higher and lower oxidation states. The lower oxo acids disproportionate because some of the phosphorus atoms attain the relatively stable +5 oxidation state. For example, orthophosphorus acid, which contains phosphorus in the oxidation state +3, on heating, undergoes disproportionation to form phosphine, which contains phosphorus in the oxidation state -3, and orthophosphoric acid, which contains phosphorus in the oxidation state +5. Also, look at the disproportionation of hypophosphorus acid that takes place upon strong heating. The elements oxygen, sulfur, selenium, tellurium, and polonium constitute the 16th vertical column or 6A group elements in the long form of the periodic table. The first 4 elements of the group are collectively called chalcogens or ore-forming elements. Because a large number of metal ores are found in the Earth's crust as oxides or sulfides. Oxygen is the most abundant element available in nature. It forms 20.946% of air by volume and 46.6% of the Earth's mass, mostly in the form of silicates and other compounds like carbonates, sulfates, and oxides. Most of the oxygen in the atmosphere is produced by photosynthesis in plants. It also occurs in the form of ozone, which is an allotrope of oxygen in the upper atmosphere, and protects us from the harmful radiations of the sun. Sulfur is the 16th most abundant element and constitutes about 0.034% by weight of the Earth's crust. In its combined form, sulfur is found in ores in the form of sulfates and sulfides. Sulfates include gypsum, CaSO4, 2H2O, Epsom salt, MgSO4, 7H2O, and barate, BaSO4. Sulfides include zinc blende, ZNS, galena, PbS, and copper pyrites, CuFeS2. Sulfur is also present in organic substances like mustard seeds, eggs, onion, garlic, wool, and hair. Sulfur is available in its free state in the volcanic areas of Sicily, Italy, Japan, America, Russia, and Iceland. Small deposits of sulfur are found in Pakistan and India as well. Natural gas and crude oil are other sources of sulfur. Selenium and tellurium are present in sulfide ores as metal selenites and tellurites. Polonium is a radioactive element with a half-life of 13.8 days and is very rare. It occurs in nature as a decay product of uranium and thorium minerals. Look at the electronic configuration of these elements. All the elements of this group have 6 electrons in their outer shell and have the general electronic configuration of Ns2Np4. Now, let's look at the atomic and physical properties and their trends in these elements. Let's begin with the atomic and ionic radii of these elements. From the given electronic configuration, we observe that due to the addition of a new principal energy level in each element, the atomic and ionic radii increase from oxygen to polonium. As you can see from the table, oxygen has an exceptionally small size. This is due to the higher effective nuclear charge of the oxygen atom. You already know that as we move down a group, ionization enthalpy decreases with an increase in the size of the atom. In group 16 elements too, the ionization enthalpy decreases with an increase in the size of the atom from oxygen to polonium. However, note that the elements of this group have lower values of ionization enthalpy than that of group 15 elements. This is because group 15 elements have a stable half-filled p subshell in their valence shell. Due to the extra stability of their half-filled configuration, more energy is required to remove electrons compared to group 16 elements. Let's now see the electron gain enthalpy of these elements. In general, down a group, electron gain enthalpy decreases with an increase in the size of the atom. Thus, the electron gain enthalpy of group 16 elements decreases with an increase in the size of the atom from oxygen to polonium. However, note that the oxygen atom has a less negative electron gain enthalpy than sulfur. This is because oxygen, due to its compact nature, experiences more repulsion between the electrons already present and the incoming electron. Due to these electron-electron repulsions, an oxygen atom has lesser tendency than a sulfur atom to accept the extra electron. Let's look at the trend in electronegativity. As we move down the group from oxygen to polonium, the electronegativity decreases gradually with an increase in the atomic size. Note that oxygen is the second most electronegative atom after fluorine. Let's now learn about the physical properties of the group 16 elements. Oxygen and sulfur are non-metals. Selenium and tellurium are metalloids, while polonium is a metal under normal conditions. As polonium is a radioactive element, its radioactive property is considered more important than its normal properties. Moreover, its availability is very less as it is a decay product of uranium and thorium. All the elements of group 16 exhibit allotropy. Oxygen has two allotropes, which are oxygen and ozone. Although sulfur has many allotropic forms, only two of them are stable, which are rhombic and monoclinic. Selenium and tellurium exist in both amorphous and crystalline forms. The melting and boiling points of the elements of group 16 increase from oxygen to tellurium as their atomic size increases. This is because, as their atomic size increases, the van der Waals force of attraction between the atoms increases. However, the large difference between the melting and boiling points of oxygen and sulfur may be explained by the fact that oxygen exists as a diatomic molecule, while sulfur exists as a polyatomic molecule. First, let's take a look at the oxidation states of the elements of group 16. As all the elements of this group have a configuration of Ns2np4 in their valence shell, they may attain noble gas configuration either by gaining 2 electrons, forming M2- ions, or by sharing 2 electrons, thus forming 2 covalent bonds. Hence, these elements show both negative and positive oxidation states. The table here gives details of the different oxidation states shown by these elements. The electronegativity of oxygen is very high, second only to fluorine. Therefore, it exhibits a negative oxidation state of -2 in all its metal oxides. Thus, most metal oxides are ionic and contain oxide ions. In addition to -2 oxidation state, oxygen shows -1 oxidation state in peroxides. Since the electronegativities of the elements decrease as we move down the group, the tendency of these elements to show -2 oxidation state decreases from sulfur to polonium. Since polonium has the least electronegativity, it does not show an oxidation state of -2. Instead, it shows only positive oxidation states. Talking about positive oxidation states, oxygen shows positive oxidation state only in its compounds with fluorine, since fluorine is the only element more electronegative than oxygen. It shows +2 oxidation state in oxygen difluoride and +1 in dioxygen difluoride. Note that oxygen does not have d orbitals, and therefore it cannot expand its valency. Hence, the oxygen atom cannot show an oxidation state higher than +2. The other elements of the group, apart from exhibiting +2 oxidation state, also exhibit +4 and +6 oxidation states due to the availability of d orbitals in their atoms. These elements show +4 oxidation state in their compounds with oxygen and +6 oxidation state with fluorine. Due to the inert pair effect, the stability of +6 oxidation state decreases, while the stability of +4 oxidation state increases down the group. Oxygen, like the other p-block elements present in the second period, differs considerably from the rest of the elements in its group. These differences are due to its small size and high electronegativity, and the absence of d orbitals in the valence shell of the atom. The important differences are atomicity, oxygen is diatomic and gaseous, while the other elements have complex structures and hence exist as solids. Formation of N2- ions. Oxygen, due to its high electronegativity, shows negative oxidation state and does not show any positive oxidation state except in oxygen difluoride and dioxygen difluoride. The other elements show +2, +4 and +6 oxidation states in addition to -2 oxidation state. Polonium does not show minus oxidation state. Maximum covalency. Due to the absence of d orbitals in oxygen, its covalency is limited to 2. But the covalency exceeds 4 in the other elements due to the availability of d orbitals in them. Hydrogen bond formation. Because of its small size and high electronegativity, oxygen forms strong hydrogen bonds, which greatly affects the properties of water and other compounds. However, the other elements in the group have comparatively low electronegativities and, therefore, do not form hydrogen bonds. Now, let's discuss the chemical properties of these elements. The elements of this group react with hydrogen to form hydrides of the type H2E, where E could be oxygen, sulfur, selenium, tellurium, or polonium. The physical states, melting points, boiling points, enthalpy of formation, enthalpy of dissociation, and dissociation constants of these hydrides are given in the table here. Let's look at the physical states of these hydrides. Water is a colorless and odorless liquid, while the hydrides of all the other elements of the group are colorless, poisonous gases with unpleasant odors. The boiling point of the hydrides markedly decreases from water to hydrogen sulfide and then increases. Water has an abnormally high boiling point because its molecules are associated with each other by means of hydrogen bonds in its solid as well as liquid states. On moving down the group, the boiling point increases from hydrogen sulfide to hydrogen telluride because of the increase in molecular weight. The thermal stability of these hydrides decreases with a decrease in the bond dissociation enthalpy of the He bond from H2O to H2Te. As can be seen from the dissociation constant values, the acidic character of the hydrides increases from H2O to H2Te. The increase in acidic character is due to the decrease in the He bond dissociation enthalpy from H2O to H2Te. Except for water, all the other hydrides act as reducing agents. The reducing property of these hydrides increases from H2S to H2Te. This is again due to the decrease in their thermal stability from H2S to H2Te. All the elements of this group react with oxygen to form dioxides and trioxides of the type EO2 and EO3 respectively, where E could be sulfur, selenium, tellurium or polonium. Both these types of oxides are acidic in nature. Ozone, which is treated as a dioxide of oxygen, and sulfur dioxide are gases, while selenium dioxide and tellurium dioxide are solids. The reducing property of these dioxides decreases from sulfur dioxide to tellurium dioxide. Sulfur dioxide is a reducing agent, whereas tellurium dioxide is a good oxidizing agent. Sulfur trioxide is the only important triode in this group. At room temperature, sulfur trioxide is a solid and exists in three distinct forms: alpha, beta, and gamma. Group 16 elements form a large number of halides of the type EX6, EX4, and EX2, where E is a group 16 element and X is a halogen. Among hexaldehydes, only hexafluorides are stable. They are all colorless gases. They undergo sp3d2 hybridization and hence have octahedral geometry. Sulfur hexafluoride is an extremely inert, colorless, odorless, and non-flammable gas and is insoluble in water. Among the tetrafluorides of group 16 elements, sulfur tetrafluoride is a gas, selenium tetrafluoride is a liquid, and tellurium tetrafluoride a solid. These tetrafluorides undergo sp3d hybridization and hence have trigonal bipyramidal geometry, in which one of the equatorial positions is occupied by a lone pair of electrons. This geometry is also known as seesaw geometry. Except for selenium, all the other elements of this group form dichlorides and dibromides. These dihalides are formed by sp3 hybridization and thus have tetrahedral geometry. The presence of a lone pair of electrons gives it a bent geometry similar to that of water. Monohalides exist as E2X2 and are dimeric in nature. Monohalides undergo disproportionation and are converted into tetrahalides. For example, selenium monochloride disproportionation to form selenium tetrachloride and selenium. The structure of these monohalides is similar to that of hydrogen peroxide with a bond angle of 104 degrees. Dioxygen is prepared by different methods in the laboratory and commercially. Let us first study the laboratory methods. The most convenient method for preparing dioxygen in the laboratory involves the catalytic decomposition of solid potassium chlorate. Manganese dioxide is used as the catalyst in this reaction. The other laboratory method is the thermal decomposition of oxides of metals from the lower part of the electrochemical series. For example, the thermal decomposition of silver oxide or mercuric oxide gives dioxygen. Dioxygen may also be obtained in the laboratory by heating the higher oxides of some metals like lead, barium, and manganese. The thermal decomposition of salts rich in oxygen, such as nitrates, for example, potassium nitrate or sodium nitrate, and permanganates, for example, potassium permanganate, also yields dioxygen. Commercially, dioxygen is prepared by either the fractional distillation of liquid air or by the electrolysis of water. To prepare dioxygen from air free from water and carbon dioxide is first liquefied. The remaining constituents of liquid air, primarily liquid oxygen and liquid nitrogen, are separated by means of fractional distillation. The electrolysis of water containing a small amount of sulfuric acid or barium hydroxide leads to the liberation of oxygen at the anode and hydrogen at the cathode. Now, let's discuss the properties of dioxygen. Dioxygen is a colorless, tasteless, and odorless gas. It is slightly heavier than air. It is slightly soluble in water to the extent of 3.08 cubic centimeters in 100 cubic centimeters of water at 293 Kelvin. This small quantity of dissolved dioxygen is just sufficient to support marine and aquatic life. It can be liquefied under pressure to a pale blue liquid by compressing the gas at 90 Kelvin. It can also be solidified into a bluish-white solid at 55 Kelvin. it has 3 isotopes forms with mass numbers 16, 17, and 18. In spite of having an even number of electrons, dioxygen exhibits paramagnetic behavior. This property can be clearly explained by the molecular orbital structure of the dioxygen molecule. Let's now see the chemical properties of dioxygen. Dioxygen is a very reactive element and reacts directly with nearly all metals and non-metals. However, it does not react directly with some metals like gold and platinum, and some noble gases like helium, neon, and argon. In spite of the great reactivity of dioxygen, some external heating is required to initiate the reaction, as the bond dissociation enthalpy of the oxygen-oxygen double bond is very high. However, as the reactions are highly exothermic, once started, they proceed rapidly without further application of heat. Let's see the reaction of dioxygen with metals. Most metals burn in dioxygen and form oxides that are mostly basic in nature. The reactions of dioxygen with metals such as calcium and sodium are shown here. Similarly, most non-metals burn in dioxygen to form acidic oxides. The reactions of dioxygen with sulfur, carbon, and phosphorus are illustrated here. Let's look at the reactions of dioxygen with some compounds. Sulfur dioxide undergoes catalytic oxidation in the presence of vanadium pentoxide to form sulfur trioxide. This is an important step in the manufacture of sulfuric acid by the contact process. Similarly, hydrochloric acid undergoes oxidation in the presence of copper chloride to form chlorine. This reaction forms the basis of Deacon's method for the preparation of chlorine, which is obsolete now. Dioxygen reacts with several organic compounds, such as hydrocarbons and carbohydrates on ignition, forming carbon dioxide and water. Now let's look at the uses of dioxygen. The main importance of dioxygen lies in its support to vital processes, such as combustion and respiration. Dioxygen mixed with carbon dioxide or helium is used for artificial respiration. It is used in the manufacture of many metals. It is used in oxyacetylene welding and metal cutting. It is used to oxidize ammonia in the manufacture of nitric acid. Oxygen cylinders are widely used in hospitals, high-altitude flying, and in mountaineering. Liquid oxygen is an important constituent of the fuel used in rockets.